What do you see? What are polar coordinates, Soma? Simply put, just in general, what are polar coordinates?
Well, I just see the theta and the r.
Yeah, the theta and the r. Okay. So if I just gave you p, x, and y here, like these letters right here, what would you think to yourself? What coordinate system is that? That's Cartesian, right? And in Cartesian land, every point on the plane is described by two numbers. The horizontal position, which is x, and the vertical position, which is y. Are there other coordinate systems? There are many, many coordinate systems. This one's really nice for a flat world, which is interesting because do we live on in a flat world? It's fascinating. We originally thought that was true, so that's kind of, I think, why we started with Cartesian mapping. We're actually spherical. So actually, one better than that for our purposes in sphere land would be, what's this called? What coordinate system am I describing with that scribbling? Polar coordinates. It's still two numbers. Instead of x and y, it's going to be theta and r. Theta and r. Theta and r. What is r going to be? What's the definition of r? If this is the point P, if this is the point U, r is 5 here. What does r represent? R is the distance the point is from the origin. Pretty straightforward. It's the distance from the origin. How many points are a distance of 5 away from the origin? An infinite number. Remember, as my aside, the number of answers to given math problems, an infinite number, none, or my favorite ones are that have answers like there are 7 answers. Those are the cool math problems I think of personally. Theta value. Can someone carefully describe for me what the theta value is? Is it a distance? What is it? It's an angle. What? It's an angle from what to what? From the x-axis to the... It's not... The r value is a distance to the what? To the segment or ray from the origin to the... There's one key thing we didn't say, though. What direction did we go in? Counterclockwise. You in the counterclockwise direction. Counterclockwise direction. So this point, 3, 4, let's say U is 3, 4 right here. If U is 3, 4, what's the distance from the origin? 5. That's a nice triangle, 3, 4, 5 triangle. Otherwise, we'd really just have to use the Pythagorean theorem. Now, if we wanted the angle measure, what function is really convenient for us? Well, it's up there already. It's tangent, right? Tangent inverse of 4/3. Is that an angle measure you need to memorize? No, but many of you might know it because you've done it so much. Anybody remember what it is? It's like 53 point something, maybe 53, maybe. I can't remember exactly. But the point is that is not something you need to memorize. You need to know that it's his tangent inverse. Okay, so here are the relationships that are really key here. You've seen things like this before. So if I have a triangle, and this is theta, and this is x, and this is y, what is cosine of theta equal to? Cosine is adjacent over hypotenuse, and this is r right there. So what's the adjacent side? So it's x over r. So what does that imply? X is equal to r cosine theta. Similarly, you therefore know that y is equal to r what? Sine theta. You're going to use this many, many times. All the time. You're going to use this a ton. Now, what do you know about the distance here? Well, it's a right triangle, so what does r squared equal? Well, x squared plus y squared. So what does r equal? The square root of x squared plus y squared. Why don't I take the negative one when I do that? Because r is always what? Positive. You don't worry about the negative. Exactly. And then we provide that x is not 0 right there. Okay, so let's go back and forth here. So what does this mean? So given Cartesian coordinates for the points with polar coordinates, r theta. Remember, r is first and then theta. So let's say p is 7 and it's pi over 3. I could ask you to, if those are polar coordinates, what are the Cartesian coordinates? Those are polar coordinates. What are their Cartesian coordinates? So what does this 7 tell us? That the point is how far away? 7. And then what's the angle measure? How many degrees is pi over 3? 60 degrees. So what does that look like? If we wanted to do this point, if we wanted to draw this point, you need to go pi over 3, which is how far? Like 60 degrees, like right about here. And then what's this distance? 7. So you know that this right here is pi over 3. And if you wanted the Cartesian here, you need the x and the y, correct? So which thing do you need to find the x coordinate? What does x equal? X equals 7 cosine pi over 3. And what does y equal? 7 sine pi over 3. You will be expected to know your basic trig values. Some of you are still working on that. Please make sure you cannot leave cosine pi over 3 in your final answer. Please don't do that. What is cosine of pi over 3? Yes. And what is sine of pi over 3? 3 over 2. Yeah. So you'd stop there. So what would the coordinates be for this? 7 over 2, comma, 7 root 3 over 2. You okay with that? Okay, what about this one right here? 5, 0. What does that mean? It's a distance of 5 away from the origin, and what's the angle measure that it forms?
0.
So it's just here. So what point is that in Cartesian? 5, 0 in Cartesian, yeah. So are some points the same? Yes, all the points on the positive x-axis. But what about 5 pi? What's that look like? Pi is all the way back here, right? So what point is that? Negative 5, 0. Exactly, so it's 180 degrees counterclockwise from the positive x-axis. Okay, what about these? Give polar coordinates for these Cartesian ones. So what about this one? Well, we just did 3, 4. What's that distance away from the origin? 5. And then what's the angle measure? Tan inverse of 4/3. Yeah. You're going to, yeah, go ahead.
You said something about not regarding the negative value of the r, but that question had a negative r.
No, it didn't. So it didn't because this is Cartesian.
Oh.
This is Cartesian. It's asking, it says give. Oh, I see what you're saying. I see what you're saying. So excuse me. You're absolutely right. So 5 pi, give Cartesian coordinates for the points. So we're giving Cartesian coordinates. That is the Cartesian coordinate, not polar. You're right though. If it was polar, that would make no sense. You could do it, but if I gave you a negative r value for polar, what do you think you actually do with the r? You flip it. So you do the positive one, and then you go 180 degrees the other direction. Not 180 degrees the other direction. So you go this and then like bounce back. Don't worry about that for now. So if this is give polar coordinates, these are Cartesian. What is 0, negative 5? Where is that? That's here, right? What's that distance away from the origin? 5, right? But somebody who hasn't spoken yet, what's this angle measure right there? 3 what? 3 pi over 2. Yeah. 3/4 of the way around 2 pi. How are we feeling about understanding what polar coordinates mean? We pretty good? Thumb up? We're pretty good? Is there such thing as polar graph paper? Yeah. What do you think polar graph paper looks like? What's it look like? Concentric circles. Looks like a bullseye, right? You have the distance 1, 2, 3, 4, 5 away from the origin, and then what do you have? All those nice unit circle radian measures. So you can trace things out or estimate them. Okay, this is what it looks like. Hey, can you generate stuff like this? Absolutely. If you go to Google and type in graph paper generator, there are really cool graph paper generators online. So if you ever want to generate backgrounds for OneNote, it's a great place to go to get. You can decide how big it is, how dense it is. It's super nice. It's super nice. Okay, get to the board, everybody, and find a partner you haven't worked with in a little while. Find a partner you haven't worked with in a little while. Buddy, do you remember what the relationships we know are? What were those key relationships? We know that r is equal to this, right? Okay, that might be helpful. But we know that x is equal to what? Cosine theta. And what does y equal? R sine theta, right? But what does it tell us? Y is equal to what? What does y equal, everybody? So where can we plug that in? Nah, not to r. Where can we plug it in? Keep on going. It's right there. Woo! So we have 1 is equal to r sine theta. So what does r equal? 1 over what? Sine theta. Your functions will generally be in terms of theta. So r theta is 1 over sine theta. Everybody get your calculator. Sit down, get your calculator, and graph this on your calculator for me. Graph this on your calculator. What does theta equal? Tan inverse of y over x. Y over x. Y over x. Careful. Careful. Okay, ready to do some more fun stuff? Okay, use your calculator and graph both of these. Use your calculator and graph both of those. If it's a calculator section, you use your calculator. There is no glory, there are no points for doing things by hand that you could do on your calculator. That being said, sometimes you will need to know what polar graphs look like. These are basic ones that you will need to know. When I say these, I mean of this form right here. So do you see this general form? You can look up the rules. I am not going to go over it now, but you need to know these. You need to know if I gave you any a value or n value, what does it look like? What does the n value do to the graph, do you think? It changes the number of petals, right? Changes the number of petals. What does the a value do? Stretches it. Yeah. So just be careful with it, but you have to remember certain things. So for example, which one is this?
2.
Which one is that? Is that A or B? It's A, right? This one's A, and this one is B. See, there's different rules for sine and cosine. You need to be very careful about it. You have to be very careful about it, okay? How many petals do you see?
Multiplied by 2.
Is it sine by 2? It's just something reflected, maybe. Look it up. There's a few rules. I'm leaving it to you, Okay, let's do the interesting stuff though. This is the interesting stuff. What do you see on the left there? And you can stay where you're sitting. That's totally fine. You don't have to move. What do you see on the left? What shape is this?
Circle.
It's a circle. What is this called? What's that called? With an S. Sector. Right, it's a sector. If I want to find the area of a sector, it's the entire circle and that piece of that circle. What is the area of this whole circle? Pi r squared. Correct? So what percentage of this circle is this? Theta over 2 pi. That's the percentage of the circle. What is pi r squared? The area of the whole circle. So if you multiply them together, you get the area of the sector. Have you seen this before? 1/2 r squared theta? Should be at least vaguely familiar to you. If not, here it is. Is this a perfect circle? No, it's a limacon. It's a kind of polar graph. It's a polar graph. You'll see it. It's, what is it? Yeah, 3 plus 2 cosine theta. This is still a sector though. What's the only difference really between this type of sector and this sector right here? Different what? Well, it's different percent, but what else? What's this and what's this? Different R values, right? Okay. So if I were to slice this up into sectors and I found the area of all these sectors, I can estimate the area of this limacon, correct? The challenge is though, are these R values the same? No. What happens as I make the theta value smaller? What happens to the R values? If I make the theta value really, really small, what happens to these R values? They get what? They get really, really close together, right? They get really, really close together. Do you remember with Cartesian functions, we broke them up into an infinite number of rectangles, and we added them together, and as we created more and more rectangles, we approached the actual area under the curve. Remember that? That's effectively half of calculus. Instead of using rectangles, what are we going to break polar functions into? The areas. Sectors. Sectors, right. And here's the thing. As we make them infinitely small, what happens? They approach, the sum of them approaches the actual area of inside. When I say inside, I mean from the outer, from the function to the origin, the area contained by the polar function. So here's the thing. What's the area of a rectangle? Well, it's base times height. Remember, it's like delta x times f of x. Instead, what are we going to use? This right here. What is r? Remember you wrote the function? Remember it was r theta? Remember it was r equals 1 over sine theta for the last one we did? You're going to use r theta. And instead of theta, theta is just going to be d theta, the little tiny, tiny slice. The integral is very straightforward. It looks like this, right here. So the area of this limacon is literally, where's that? Oh, that 1/2. What was that? Remember that was 1 over 2 pi right there, remember? And what's this? What was it? 1/2 r squared theta, remember that? 1/2 r squared theta, the pi's cancel. So you have 1/2 r squared. R was a function in terms of theta. You square it, and where's that d theta? That's the little tiny slice you're taking. Generally speaking, this is just my opinion, but I think it's the most challenging part. What do you think the hardest part of writing this integral is going to be?
From which part?
Exactly. You are not scanning from left to right anymore. What are you doing? You're going from R to R. It's not left to right. You can think of it as sweeping out the area. It's sweeping out the area. So generally speaking, be really freaking careful because like with parametric equations, can you go too far? Can polar equations overlap? Like those flowers that you drew before, if you change the R values from like 0 to 2 pi, it goes once around. But if it goes 0 to 100 pi, what happens? It looks the same, but what's actually going on? It's just repeating. So is it really easy to over count or under count? Absolutely. So I could ask you this. See that petal right there? I could ask you, what's the area of this petal? Well, let's set up the integral here. It's going to be just 1/2 the integral of f of theta. Well, does it give you f of theta? Yeah. What is it? 3 sine 2 theta. What do you do to that?
Square.
D theta. But what have I not written in? Alpha and beta. The starting R value. So where does this start? It starts at the origin. By the way, are there multiple ways you can start in this? Probably. Be careful. What's the easiest one? Where does it start? If you're at 0, what's the distance from the origin?
0.
And what's the angle measure? So what's the lower one going to be? 0. Nice. So as you're traveling around, this point takes off, right? Here's this point right here. Change color a little bit here. What's happening to the theta value as this point keeps on traveling? Is the theta value getting bigger or smaller? Bigger. It's getting bigger. What do you think that, you want to estimate what that point is? That's a fun point to find. What do you think that theta value is? Pi over 4. And then R value gets smaller, but what's happening to the theta value? It's getting what? It's getting bigger. It keeps on going down, it keeps on going down. What's it eventually getting to?
Pi over 2.
Exactly. Pi over 2. Here's the thing. You're like, ah, I've got this integral expression. I'm pretty much done. You're like, 9 over 2, Aww. Why am I sad? It's correct, but is that an easy thing to integrate? No. You are going to get a bunch of these when you have your calculator, everybody. You know how to do that. Do you remember how you do that? Anybody remember what you have to use? You have to use what? No, you can do it on your calculator pretty easily. That's fine. Yeah, you have to do parts, and then you have to do like a couple layers of it, and then move something over. You get back to cosine squared, and then get back to sine squared. You move it over. So is it doable by hand? Yes. If you have your calculator, stop there, type it into your calculator, and go to 3 decimal places. You okay with that?
3? Did you say 2 or
3? 3. Always 3. Always 3. Why always 3? That's what they require. If you don't go to 3 decimal places, they don't count the point, the answer point. Don't lose that easy point. So on questions like this question actually give us 0 to 2 pi. I didn't scroll down that far. But if they give you 0 to 2 pi, that's awesome. A really common question is state the integral, but do not evaluate the integral that represents the area of this pedal. Okay. So if I asked you what's the area of the entire shape, you would just take that and multiply it by 4. There's lots of symmetry. There's lots of symmetry. There's lots of symmetry. So area, relatively straightforward. Now let's talk about slope. How's this look right here? Oh, it looks so terrible. Mr. Seaman, it's so bad. It's so bad. Well, you've seen this before, everybody. dy dx, if y is in terms of theta, dy dx is just dy d theta. And what is dx? Dx d theta. You've seen, this is not new, everybody, right? You know that x is equal to r cosine theta. If you have r in terms of theta, what can you do? You could put f of theta right there. And then, is this all in theta? Uh-huh. So can you find dx d theta pretty easily? Yes. Can you find dy d theta pretty easily? Yes. So therefore, can you find the slope dy dx pretty easily? Yes. Algebraically, it's easy. Does it mean it's super fun? Not always. Here's what I mean. If I asked you to find the slope of that curve right there, you'll see what happens. Give it a try right now. Try to find a new partner. Try to find the slope of that. So you might have ended up with something like this. What do you have to do first? You have to use the product rule to find the derivative of x and y in terms of theta, right? And what do you end up with? Something big and something big? Agreed? Be real careful. Get some 6's in there. The challenge is that after you do that, what do you have to plug in? Pi over 3. Is that kind of annoying? It's not impossible. It's kind of annoying. It's not impossible, but is it really easy to make a small mistake? Super easy. Are you comfortable with the process, though? Do you understand what you're supposed to do on these? Slope is dy dx. You need y in terms of theta and x in terms of theta. Nice. What's that in the box right there? Arc length. Hey, look familiar? Yeah, it's really, 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 really familiar. Again, though, just like with parametrics, what do you think the hardest thing is going to be to find? Alpha and beta, A and B, alpha and beta, right? Now here's the thing. If you have your calculator, use it. So for example, have you already found dx d theta on this? Yeah. Have you found dy d theta for this one? Yeah, you have. So if I ask you, find the arc length of one pedal, we already know what the graph, it's like one nice pedal, right? Oh, what's the integral going to look like? You ready? Yeah. Why is it that horrible? It's that horrible because what is this? Is this dx d theta? And that's dy d theta, right? Do you do that by hand? No. 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 Even plugging that into your calculator's mind kind of a pain in the butt, right? So are you going to have to do something like that by hand? No. But could you be expected to get that, clean it up a little bit, and then see it on a multiple choice? Absolutely. Moral of the story is if you have your calculator, what should you use? Yeah, please, 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 please.